Now I want you to ask me many questions on implementation of this. So if we have been orienting this course, even the third semester course and this course, wherein we are talking about implementation. Now what are all the questions you have in mind? Now I have given you a very colorful slide, okay. Get out some questions from this. How do you go ahead and implement this?
If the RAM is full, which page do we?
That's a bigger question, right? If the RAM is full, which page will do? If the RAM is full, which page will I do? So what is your answer?
One that is.
So question number 1, if RAM is full, what will you do? What will you means what? What will the OS do? Okay? What will it do? What can it do? So you got the question, very interesting question. We'll as your thought process goes, we will orient the class. I don't want it to go by my thought process. So imagine there are only 6 pages here, right? 0 to 5. Now this program has 7 pages. Now he has loaded P4, P1, P2, P3, P4, P5, P6. Now 7 wants to enter. Where will I load it? This is very important question, very excellent question. Now you tell me, what will you do anyway? We have to remove something and put this. Okay. So I have to replace something. So we follow what we call as a page replacement. Okay. Correct? I have to replace something. So I will do a page replacement algorithm. So there are a lot of page replacement algorithms. Now I will teach you some page replacement algorithms also. But the OS course is expected you will learn many more page replacement algorithms. But I will give you a gist of many things there, right? So about page replacement algorithms. Now, what should be the so I replace some page. So the next question is, immediate obvious question is, which page to replace? Correct? That's the immediate. So this is the only question that this fellow answers. So this which page to replace? I replace that page, I replace this page, everything became a paper. Okay, so that's the thing. So which page to replace? Which page to replace? There are hundreds of papers. Okay. Now there is one sensible thing which they call it as least recently. They call it used, but I call it accessed. That makes sense. Okay. They say LRU, I say LRA. Okay. Least recently accessed. Some page which I did not touch in the past at all. Okay. Then neglect it. Right. You can replace that because there is no chance that you will go and touch it. Who is telling this? Which property is telling you this LRA will work nicely? Temporal and spatial locality. Temporal locality in particular. Okay. Because in the recent past I have not touched that page. So my chance that I will not touch that page is going to be less, right. So this will all, so you ask the programmer to write his own program. See, so I can write a program that will go and completely kill this page replacement policy, right. We can write programs, we will give you some examples, we will also ask you some quiz questions also in that, okay. But on the other hand, if you write, normal fellow writes a program with sane mind, okay, then this least recently accessed will work perfectly well. There is no necessity for any more research in this. Okay, so that is the thing. Now we will, so how do you implement least recently accessed? Okay, so we will, the same thing will happen. Whatever I am going to teach here, why I started with memory is that whatever I am going to teach here will also be applicable in the case of cache memory, right, which is going to be close. Now we are talking about RAM, right, all these things are happening in RAM. We will now talk about the same thing in cache memory. There I will tell you how to implement this LRU etc. at the cache level. But this is a which page to replace is something, and who will execute this page replacement algorithm? Operating system, that is a general name, the interrupt service routine, which is the page fault handler. Okay, let us be explicit. Okay, page fault handler. Operating system covers everything, right. Okay. So the page fault handler will be responsible for doing this page replacement. Okay. Next, 2. There is a much more fundamental question, right. What's a much more obvious fundamental question? Hey, come on here. Obvious question. Where will this page translation table be loaded? Correct? Is it going to be separate hardware? Or is it going to be? So where was the segment table loaded? In the RAM, right? The segment table which segmented the memory was itself in the memory. Okay, you got this, right? You have done segmentation. So if you had done your first assignment very well, understood and did it, okay, then you will appreciate the fact that the segment table which was describing the different segments in the memory itself is inside a segment. Okay, you got it. So that's how first the operating system will fix it. Like that, the entire page translation mechanism will be there in the RAM. Okay, right? So now we will go into step by step delineation. So this is a question. So the second question what we want to load is, where will the page translation details be loaded in memory? Okay. Where will it be loaded in RAM? So yes, so this is the RAM, this is the virtual address space, big one, this is the logical address space, this is the physical RAM. The operating system will load the entire table here. This is basically a table, right? The entire table in this RAM. And then such that, say, let this be some k to some t, so that let there be some pages here. So for these pages, so if I generate a address k, it will look somewhere inside this table, right? If I generate the address k, it will look somewhere in this table, right? That itself will be, so all these pages like k to t will be permanently loaded into your physical memory. So these things will be permanently loaded in some say some page frame, say frame k to frame t. Okay. So I will create a space in the, so when you do the assignment this becomes extremely clear, okay, but till you do the assignment I will try and make the best to. So the entire page translation mechanism will be loaded into the memory, okay, and will be allocated a space in their virtual memory, and that will spawn some several pages, and all those pages will also be permanently loaded in your physical memory. Why should it be permanently loaded in your physical memory? Well, otherwise I can't do the translation. Right? The table needed for the translation is not there in the physical memory, then I am gone forever. Right? So this is the crux. So this is something which none of these books teach you. So these are some things that we need to keep in mind and apply, and that only comes when you do the lab in much more detail. But please understand that my page translation mechanism that we are seeing here, this is basically a table like your descriptor table, etc., and this table will have a space in the logical address space, right, which will spawn across multiple page frames, and all these pages which are there, which will contain the information of this page translation, should be permanently residing in the physical memory the moment I enable paging. You understand this? Do you follow or not? Right? Otherwise what will happen? I can't do the page translation, right? Okay. Now let us go and see. We will do a very simple thing today. Now I have 2 power 32 bytes in my virtual address space. Okay. Now there are each page I have made it as 2 power 12 bytes. Okay, each page I have made it as 2 power 12 bytes. So I have 2 power 20 pages. So you got it? So given a 32-bit address, how will I find which page it belongs to? Right? If given a 32-bit address, let me say B31, B32, B1, B0, B1, B2, B11, B12 and all. Which page does it belong to? B31 to B12, because each, sorry, please understand that each page is 2 power 12 bytes. So the page number of a given address is given by the most significant 20 bits. Are you all able to find out? Are you able to follow? Page number of a given 32-bit address is the 20 most significant bits. Namely B31 to B12. Correct? So I have a table. This table will have 2 power 20 entries. It will have 2 power 20 entries. So in this 2 power 20 entries, each entry will, so one entry per page. Okay. So this fellow will have 2 power 20 entries, one entry per page. Okay. So one entry per page. So what will be that entry? It will tell you if at all that page is loaded in the RAM, where it is loaded. So what I do when I generate an effective address, I take the first 20 bits and I go into this table, index into this table, and when I index into this table, what it will tell me? If at all that particular page is loaded into the RAM, where it is loaded, the address to which it is loaded. So it will store a 4-byte address, because this is a 32-bit RAM, right? So I have to store a 4-byte address. So totally how many things I need? I need 2 power 20 entries into 4 byte is 2 power 2, right? So I need 2 power 22 bytes to store this entire table. Each page frame is what? 2 power 12 bytes, right? Each page is 2 power 12 bytes, right? So I need 1024 pages to store this. Are you getting this? So what I do, when I generate a 32-bit address, 32-bit logical address or 32-bit effective address, I add to the segment base, etc. I generate a 32-bit effective address, in which the first 20 bits will tell me which page I belong to. The remaining 12 bits is an index into that page. So I take the first 12 bytes, first 20 bits and I index into this table. This fellow will tell if at all I am loaded into the memory, it will say where I am loaded. For each of these pages it will tell me. So I go to that address, so that will be a 32-bit address. So let us say this page is loaded here. So I have a 32-bit address where this is the 20-bit and 12 bits. So this will tell me the base of where it is added, and I will take this 12 bits as an offset here and I will index. So this is the actual address which I need to access. Is this clear? So it is a very simple thing. So I take the 20 bits, I index into this table, there are 2 power 20 entries. So for each of the combination of these 20 bits I will have an entry. I will go to that entry. In that entry it will tell if at all the page is loaded, where it is loaded, it will tell me the starting address in the RAM. to that I will add this 12 bits whatever that offset given by the first 12 bits, and that will tell me exactly what that address is.
So,
Right.
each entry 4 bytes.
Because it's a 32-bit address, no? RAM is 32 bit. So I can essentially have 4 GB also fully. Because it's a 32-bit address space. I could have 4 GB, now I have 2 GB.
Sir,
Yes.
you
Yes.
mentioned that the table cannot be there in the disk, should be on the RAM.
Table should be, wait 1 minute, the table should be in the disk and also in the RAM.
Yeah, why should it be loaded in the RAM?
Because when I want to access the architecture can see only the RAM. It cannot see the disk.
It should be in the disk.
When I want to do a translation, right? See, you are in an instruction, when you are executing the instruction, at least 3 times you are touching memory to fetch the instruction, to fetch the data and store back the results. So in the real worst case, you will be touching the memory 3 times. Every time when I touch, whatever the CPU is generating is only an effective address. That effective address has to get translated into a physical address. So 3 times when I go and access a disk for every instruction execution, you go mad. Right? First it will become extremely slow. Second thing is accessing a disk, you have to execute a program to access a disk, which is called a disk driver. So you cannot, as a CPU, I cannot access some byte in the disk directly. I have to go to the device driver of the disk, which will know how the data is organized in the disk, and it will fetch for me. And that device driver or the disk driver itself is a program. So for me to execute one instruction, if all these this table is there in the disk, I have to know how I am going to translate. So at least for every time when I am accessing and when I am executing an instruction, 3 addresses I need to translate in the first case. For just translating these 3 things, if I am going to execute that device driver program 3 times and go to the disk and get it, then it is going to become extremely complex. Are you able to appreciate that? So my entire page translation has to be loaded into the RAM, and I will look at the RAM and basically do the translation. I can access the RAM as a CPU without executing another program, but I cannot access the disk as a CPU without executing the device driver. Okay, right? So to access the RAM from the CPU, I need not execute another instruction. The same instruction itself can go and fetch the data from the RAM. But for me to access data in the disk, I have to execute another set of instructions to get it. So that is why when I want to execute something, that has to be available in the RAM. It cannot be from the disk, I can't directly take it, execute. Of course you can do some raw mapping and all, but those are all crazy things. That will kill your performance. Are you able to follow? Okay, good. Now just finishing this, I have this in the RAM. So I generate, so as a CPU I generate a 32-bit address. I take that 20-bit, index into this table. So somewhere some table should store the start address of this. So in the Intel architecture there is a register, control register called CR3, right? There is a control register called CR3. That CR3 will load the start address of your memory. You are able to follow? So in that CR3, so what I do, when I generate a logical address of effective address of 32 bits, I take the first 20 bits and I index into the table starting at the address given by CR3. So I come to that entry, there I find out if it is loaded, then I get that 4-byte address. So I go to that address, I add these 12 bits, which is the offset, and that will give me exactly in the RAM which memory location I need to access. Right? To access this table cannot be accessed if it is in the disk. So this entire table, that is that set of 1024 pages, that 1024 pages should be available on the memory, and the start of the table will be given by CR3. So when I generate an effective address, I go to the CR3, I get the, I index this 20 bits into the table and I access the RAM to get that 4 byte. That 4 byte I add that 12 bits offset, and that again I go to the RAM and fetch the data. You are getting this? So this is the overall. So I said if the page is loaded, then I am taking 4 bytes. How will I know whether the page is loaded or not? That's your question, right? Think, search a bit. You have already done something similar in segmentation. Okay, right? A segment selector. There is some last 3 bits, right? What are those 3 bits used for? Some privilege level, low LDT, GDT, right? You don't need to specify those last 3 bits are anyway 0 and you are using it for some other purpose. Like this, can I use something here? Okay, that's a clue. Okay, right? So we sign off now with saying that there is a base address CR3, the entire 1024 pages are available in the memory, and then if the page is loaded, it will give me a 4 byte address to which I will add the 12 bits to find the exact location. Okay. Now what has happened now? Memory access, RAM itself is a killer. Now to find, first when I have to go to a table, from that table I have to get some address, and from that address I have to add something, again I have to go and access. So one access has now become 2 access. More interestingly, we saw, right, in the case of segmentation what has happened? So let us say, so when I generate a logical address, it goes to the GDT, gets that segment base, add it, it generates an effective address. Now this effective address, you take the 20 bits, go somewhere, get a base, get the base of the table, add the 12 bits, then you go and access. So by the time I see that whatever I want to access, I have gone through multiple memory access. So to solve all these problems, we had the notion of a shadow register. So you all understood what is shadow register in segmentation, correct? So the shadow register reduced that access, and because of shadow register we had some issues, right? What was the issue? If I go and change something in the GDT, it will not reflect, again I have to move. Okay. So now like shadow register, we will also have something here, right, page translation buffer, so many things, so some of the architectural details. If you do not have those shadow register or anything, the simple one memory access, which itself we considered as a monkey, now becomes 3 memory access. So one memory I can say became mad, second memory it got hurt, third memory it got drunk or bit by a scorpion. Okay. So this monkey becomes extremely crazy. Now 2 things that we need to keep in mind from your implementation point of view, we need to say, should I have all these 1024 pages? Can I do a demand of the demand paging, something like that, okay. What we thought sort of demand paging, we said demand paging is that whatever I need, I want to load it whenever I need it. So can I do something more on reducing this number of 1024 pages? That is another thing. The other important question is, how do I store information whether a page is loaded or not? Then we will see how these things are managed. So we will get it. So at the end of this lab 3, you will be setting up a page table, you will be accessing one by one, you will generate a page fault, you will do several things as a part of that third exercise. Okay.